Welcome to the deep dive. Today we're looking at something, well, really unexpected. How a material we've known for thousands of years is shaking up advanced medical tech.
It's a fascinating story.
We're talking about silk.
Yep, silk. And how it's playing a surprising role, not just in things like fiber optics, but specifically in how we study the brain. Okay, let's get into it.
Absolutely. So, one of the biggest challenges in neurotechnology, when we want to understand brain circuits, has always been the tools themselves.
The probes.
Exactly. The probes we use to listen in on neurons are typically quite rigid, think metal or stiff polymers.
Okay.
But the brain is incredibly soft. So you have this fundamental mismatch, this mechanical difference.
Like putting a stick into jelly.
Pretty much.
Yeah.
And that mismatch causes real problems over time. Chronic damage, inflammation, scarring around the probe.
Which makes it hard to get reliable information long term. Yeah.
Precisely. It's been a major roadblock for studying brain function over weeks or months, or for developing lasting interfaces. So that brings us to this new approach, the Silk-Optrode, they're calling it. How does Silk solve this?
Right, the Silk-Optrode. It's ingenious because it leverages silk's unique combination of properties.
Like what? We know it's strong, but...
Well, yes, but also it's highly transparent to light, which is crucial for optical applications. And it's very biocompatible. The body generally accepts it well.
Okay, useful for implants.
But here's the really clever part. Its mechanical strength isn't fixed. It's controllable.
How so?
The silk fiber they use is designed to be relatively stiff when it's dry. Stiff enough, actually, to be inserted into the brain tissue accurately with minimal trauma. Kind of like guiding a very fine needle.
Ah, so it's firm enough for the insertion process.
Exactly. But then, and this is the aha moment, once it's implanted and comes into contact with the cerebrospinal fluid in the brain.
It hydrates.
It hydrates, and its stiffness just plummets. The Young's modulus, which is a measure of stiffness, drops by over 90%.
90%, wow.
Yeah, it goes from about 38.7 megapascals down to just 3.5. And its bending stiffness, how easily it flexes, reduces about 11 times, becomes incredibly soft and flexible.
So the probe basically adapts itself to the brain environment after it's put in.
That's exactly it. It actively conforms to the soft tissue around it.
That sounds like a huge advantage. What does that mean in practice for the tissue damage problem?
It means significantly less mechanical stress on the surrounding brain cells. Less micromotion, that tiny grating movement between a stiff probe and soft tissue that causes so much irritation.
Right.
And the result, shown in studies, is a much better interface long-term. Significantly less immune response, less glial scarring, fewer tissue lesions compared to traditional stiffer materials over periods like 2 months.
Okay, that's a massive improvement for chronic studies. Now, the probe itself, the Silk-Optrode, it's not just the silk fiber, is it?
No, it's a hybrid. It cleverly combines that natural silk optical fiber core with these ultra-thin, flexible microelectrode arrays wrapped around it.
And they packed a lot onto it.
They really did. We're talking 128 recording channels on a single, very thin probe. And they managed this without making it significantly thicker. Plus, the optical loss is very low, around 3.08 lb per centimeter, so the light signals for stimulation get through effectively.
So you can stimulate and record.
Simultaneously, that's the key functional advantage. You can use optogenetics using light to activate or inhibit specific neurons.
Which requires that optical fiber.
Right. And at the same time, you use those 128 channels to record the resulting electrical activity from lots of nearby neurons. And crucially, because the stimulation is light-based, you don't get the electrical artifacts that mess up recordings when you use traditional electrical stimulation.
Ah, I see. Cleaner data because the stimulation method doesn't interfere electrically.
Exactly. Much clearer insights into the neural responses.
And they showed this working in animals. You mentioned a specific example.
Yes. In studies with mice, they used the Silk-Optrode to stimulate neurons in the medial prefrontal cortex, an area involved in things like decision-making and anxiety.
And what happened?
They found that the stimulation actually influenced the mice's behavior. They moved faster and spent more time in the exposed central area of an arena. Suggesting it had a positive effect, potentially reducing anxiety-like behavior. It's a powerful demonstration that the probe is stable, biocompatible, and effective enough to both modulate and record complex neural activity related to behavior over time.
And presumably much better tolerated than older tech.
Definitely. The studies consistently show less glial scarring and microglial aggregation signs of chronic inflammation compared to, say, standard quartz fibers, which are much stiffer.
So taking a step back,
Yeah.
what's the bigger picture here? This silk technology seems really promising.
It really is. It opens up completely new possibilities for developing more sophisticated, multifunctional tools for neuroscience. Think advanced brain-computer interfaces, or probes that can deliver therapies and monitor their effects long-term. It could lead to a much deeper understanding of neurological conditions and potentially new ways to treat them.
So, for you listening, this is a fantastic example of how thinking creatively about materials, even ancient ones like silk, can solve really tough problems in modern medicine.
It pushes the boundaries of what's possible in interfacing with the brain.
It makes you wonder, doesn't it? Imagine the potential unlocked by this simple, natural fiber. What other unlikely heroes from nature might just be waiting to revolutionize our technology and medicine?